Okay, hi everybody, it's Mr. Murray back again, and I have a second lesson here for you. Today's lesson is 6.2, Binomial Distributions. So if you remember, last lesson was probability models, and I introduced to you the concept of a distribution table or a distribution chart, and we also talked about the expected value or the average value. What we would expect to see when an experiment is performed many times. So today we're going to get into what's called a binomial distribution. That's a specific type of distribution. And in order to understand it, we're going to have to go through a bit of definition here. So a stochastic process, this is how you pronounce this, it's a stochastic process, is a sequence of experiments that depend on some chance element. They are referred to as repeated trials if and only if the experiments are identical, they're exactly the same way in every way, and the experiments are independent. Repeats don't affect any other trial. For example, tossing a coin 50 times, yep, they're identical and independent. Rolling a die 10 times, selecting a card only if that card is replaced each time, those are all stochastic processes and repeated trials. A Bernoulli trial is a repeated trial in which there's only two outcomes. Either you succeed or you fail. So Bernoulli trial, two outcomes, success or failure. So let's take a look at example 1. Calculate the probability distribution for the number of heads. Okay, I'm going to underline that. That's my X for sure. When you toss a coin 3 times. Okay, well, if we're going to figure this out, it might be easier if we actually draw a tree diagram first so that we can see all the different outcomes that are possible here. And we all know that the first flip could be a head or a tail, second flip, head or a tail, third flip, head or tail. And if we draw that tree diagram first, knowing that each of these outcomes has a 1 in 2 chance all the way down. 1 in 2 chance of flipping a head first, 1 in 2 chance of flipping a head second, and a 1 in 2 chance of flipping a head third. There are a total of 1, 2, 3, 4, 5, 6, 7, 8 outcomes here. And out of those 8 outcomes, the ways that we can get 0 heads, X is number of successful things, heads in this case, 0 heads would be tail, tail, tail. So the probability of that is 1 in 8. The probability of 1 head exactly, well, let's think about it. You could get head, tail, tail, that's 1 head, or tail, head, tail, that's 2 heads, or tail, tail, head, that's 1 head. And I don't think there's any other options here, so that's a 3 in 8 chance. What if we got exactly 2 heads? There could be head, head, tail, or head, tail, head, or tail, head, head. That's a 3 in 8 chance as well. And the last one says, what if we got all 3 heads? Well, that's 1, 2, 3 head, head, head in a row. That's a 1 in 8 chance of that happening. Okay. Let's take a look at the expected value now. The expected value from this, if we look at x times px, is 0 times 1 in 8, which is 0, 1 times 3 in 8, 2 times 3 in 8 is 6 in 8, and 3 times 1 in 8 is 3 in 8. Well, that adds up to 6 plus 6 is 12 in 8. So the expected value is equal to 12 in 8, or 1.5. 1.5 what? Heads per 3 flips of a coin. Now, does that make sense to you guys? That you would see, on average, 1.5 heads every time you flip a coin 3 times. Well, it makes sense. That's half as many, right? If we're going to see half as many heads and half as many tails, well, if we flip a coin 3 times, 1.5 heads makes perfect sense. Okay? Next. Conclusions. What do I notice about the patterns here? I know that there are 8 total outcomes, which, by the way, is 2 to the 3 equals 8 outcomes, right? There are 2 choices per event. There's 2 choices here, 2 choices here, 2 choices here. 2 times 2 times 2, or 2 cubed, is 8. I wonder if there was 4 flips, if that answer might be 2 to the 4. Yep, it is. 2 to the 4 is 16. Okay, so that's one outcome, or one conclusion. Another conclusion is, it looks to me like the probabilities are symmetrical. Very symmetrical. In fact, so symmetrical that when I look at these numerators for the probabilities, 1, 3, 3, 1, you'll see a very important pattern there. 1 and 8, 3 and 8, 3 and 8, 1 and 8. Looking at those numerators, what do you see? Yep, you can't get away from him. It is Pascal's triangle, for sure. 1, 3, 3, 1 happens to come from the third row of Pascal's triangle. Interesting. Well, we might now have a faster way of calculating these probabilities then, if we know that we can use Pascal's triangle to generate the numerators. Very good.